Thank you for tuning into this lecture on the use of atomic force microscopy for the characterization of extracellular vesicles, or EVs. I'm Daan Vorselen, and I'm an assistant professor at Wageningen University and Research. And in the past, in my research, I have focused on describing the response of both artificial vesicles and EVs during AFM measurements. Firstly, what can you do with AFM? AFM is a scanning probe technology that allows you to image the topography or surface of particles that are attached to a substrate. So it allows the measurement of their size and their shape. A unique capability of this instrument is that it also enables the mechanical measurements of nanoscale particles, including EVs. So the resolution of this technique for imaging can be extremely high, and under specific conditions can be a fraction of a nanometer. It is thus small enough to easily detect the smallest of EVs. However, this comes at the cost that imaging is relatively slow, with images being built up 1 pixel at a time, and the throughput is not as fast as, for example, optical microscopy. An indication of the achievable amount of particles per hour are given on this slide. In principle, AFM measures any particle, but it can identify EVs based on the mechanical behavior that the particles show, but also when the technique is combined with, for example, fluorescent microscopy, or when using functionalized tips, EVs or even subsets of EVs can be detected. So AFM works differently than optical microscopy and electron microscopy. Specifically, it doesn't use lenses, and hence the resolution is not diffraction limited. Instead, it is a form of scanning probe microscopy which gathers information by physically feeling the surface. So this feeling is performed with a sharp tip, and this sharp tip is mounted on a flexible cantilever. And the cantilever can now bend due to the forces between the sample and the tip that arise when the tip comes in close proximity or is touching the surface. The amount of bending of the cantilever can be read out by pointing a laser at the cantilever end. And the reflected light will then be caught onto on a detector. So finally, a piezo can be used to either control the sample position or the cantilever position in X, Y, and Z. And this allows the scanning of the sample surface. So during the scanning, the height of the sample it can be acquired at each position, which ultimately results in the image of the surface. Importantly, AFM can be used both in air as well as in liquid environments. When working with EVs, I would strongly recommend operation in liquid because this more closely reflects the physiological environment of the EV, and working in air can substantially affect your measurements. So for imaging, it's important to know that AFM can be used in multiple modes. The simplest is called contact mode. In this mode, the tip is simply dragged along the surface while the tip height is adjusted to maintain a constant deflection of the cantilever. So this mode results in both high forces normal and parallel to the target surface, and therefore it is really not ideal for soft samples like EVs. Another operation mode is tapping mode, and this one is more frequently used for soft biological samples. In this mode, the tip is actually, the cantilever is oscillated close to its resonance frequency using a piezo. And the interaction with the surface will actually affect the amplitude of this oscillation. So in this mode, instead of maintaining a constant deflection of the cantilever, the amplitude of the oscillation is kept constant. So overall, this mode results in much lower forces between the tip and the sample because the contact time between the tip and the sample is much lower. And this also affects the forces parallel to the surface because the tip is mostly moved sideways to go to the next pixel while it's not in contact with the sample. However, maximum exerted forces are still not very well controlled in this imaging mode. A final mode that I would want to mention are kind of hybrid modes, and they are called sub-resonance tapping modes. So these modes give you both good control over normal and parallel forces, and they work by still oscillating your tip or your cantilever, but below the resonance frequency. And now, why I call it a hybrid mode is because you still read out the deflection of the cantilever instead of the amplitude of the oscillations. So in addition, this mode actually also allows you to obtain sample mechanical parameters during imaging. And I will get back to that at a later point during this presentation. The main downside of this imaging mode is that it's considerably slower than tapping mode. So here are some examples of images of EVs derived from red blood cells and obtained by AFM. On the top right, you can see an overview image with multiple vesicles on the surface, and below you can see an image of a single vesicle. The color indicates the observed height. So from these images, we can obtain, for example, the diameter and the size of these vesicles, but we can also find their shape. For example, how spread out they are on the surface. So we can derive the diameter and the shape, and we do this by measuring the entire surface of the particle through physical contact. So to derive the original size of the vesicle, we assume a certain shape of the resulted vesicle on the surface, and we also need to make some assumptions such as surface area conservation. So the size measurements depend both on the proper calibration of the step size of the piezo elements that are used in the AFM, as well as the AFM tip size. And both of these are typically provided by the manufacturer of the AFM and the tip. To obtain good estimates of vesicle size, there are a couple things we need to take into account. Firstly, AFM types have a finite tip size themselves. And everything you image is not only the sample, but is a convolution of the sample and the tip size. So if you have a very small sample, as shown here on the left, you actually mostly image your AFM tip size. The resultant image is mostly reflecting the AFM tip. Whereas for when the tip is small compared to the sample, you mostly image your sample. For vesicles or for EVs and the typical tip size used for AFM, we can't completely ignore the tip, especially not when the vesicles appear rounded on the surface, as you can see here on the right. So it is important that for AFM measurements, we need to attach the vesicles and EVs to a surface. For this end, we often use clean glass slides or mica surfaces, which are really flat. If we don't do this, we would just push around the vesicles by the forces exerted by the AFM tip during imaging, and so you wouldn't be able to image them. So attachment can be, for example, achieved based on electrostatic interactions, or also via a specific molecular interaction if you coat your surface. So this attachment has consequences for the EVs. Namely, they will deform from their original spherical shape in suspension, and they will flatten a bit on the substrate. And the degree of this flattening depends on both the stiffness of the vesicle as well as the strength of the adhesive forces between the surface and the vesicles. So for a strong adhesive interaction or for softer EVs, you will see more spread out shapes. However, independent of the exact degree of spreading, the expected shape of the vesicles or EVs is that of a spherical cap. So to accurately measure the vesicle size, we need now to measure at least two parameters, such as the height and the width of the adherent vesicles. So neither of these measures directly corresponds to the radius of the vesicle in solution, but using some basic math and assuming volume of surface area, not volume conservation, we can then calculate back the original vesicle size in solution. So why we need to assume surface area and not volume conservation is because of a fundamental property of membranes, and they are essentially barely able to stretch. So they can't really change their surface area. But EVs could lose part of their volume during adhesion to the surface by leaking water over the membrane. So a straightforward way to approximate the original size of the vesicle or EV in solution using the height measurement and the width measured at the half of the maximum height is given in this formula below. So this formula takes into account the spherical cap shape, assumes a surface area conservation, and also accounts for the tip radius. Finally, particles, including EVs, will also deform due to the forces that are exerted by the AFM tip on the particle during imaging. We have previously shown that even small imaging forces can lead to an underestimation of vesicle size by 50%. And this is why it's so important to minimize forces between the tip and the sample during imaging. For example, using sub-resonance stepping modes. Together, without the tip size and surface spreading corrections and minimization of imaging forces, EV size measurements using AFM more reflect an order of magnitude estimate than a precise measurement. However, if you take proper care, size measurements can be far more accurate and give sample averages within 10 to 20% of those obtained using different techniques, using, for example, dynamic light scattering for the size determination of vesicles. So the second property that AFMs can measure are the mechanical properties, such as stiffness and other elastic properties of vesicles. Since these parameters may perhaps be less familiar to you than size or biochemical properties, I briefly want to go into their biological relevance. So the mechanical rigidity of EVs may, for example, affect the uptake by cells. Multiple studies have by now shown that stiffer particles or vesicles may be taken up more efficiently by cells than softer ones. In addition, stiffness of excreted EVs may also be affected between healthy and diseased cells and could therefore potentially serve as a biomarker. However, mechanical characterization of vesicles and EVs is still in an early stage of development, and currently analysis methods aren't completely standardized. So how do we derive mechanical properties using AFM? The simplest and most familiar AFM or mechanical property that I will discuss is just simply the stiffness, which is similar to a spring constant. But AFM can also be used to derive specific elastic moduli, such as the Young's modulus or membrane bending modulus, which we will discuss in the next few slides. So AFM measures these parameters by measuring the resistance or force upon mechanical deformation of the vesicle. And this mechanical deformation is typically done by indentation of the EV with the AFM tip. For derivation of elastic moduli, we often also require the vesicle or EV shape. The derivation of mechanical parameters involves various assumptions, which strongly depend on the indentation model, and which I will get back to in the next few slides. Finally, we require still the calibration of the piezo step size, as similar as for imaging, but now in addition, we also need to calibrate the cantilever stiffness and the cantilever deflection sensitivity. So the cantilever stiffness is often provided by the manufacturer, but the deflection sensitivity, which is a measure for how strong of a signal you see on the detector based on the bending on your cantilever, is, for example, depends amongst others on the position of the laser spot on your cantilever. So this one you have to calibrate for each individual experiment. So most commercial AFMs have implemented straightforward and user-friendly procedures to determine both the deflection sensitivity and cantilever stiffness. As I mentioned, mechanical measurements are typically performed by controlled indentation of the vesicles. You will likely first want to image the particle of interest, determine its center position, and then move the AFM tip to this center while slowly lowering it. In that center position, you can then lower the AFM as illustrated here on the left. And by tracking the deflection of the cantilever and knowing the cantilever stiffness, it is then possible to determine the forces between the tip and the center. So the result of such an experiment is a force deformation curve, such as shown here in the middle. So in red, we can see that the force is initially zero while we lower the AFM tone. But then when we, for the first time, touch the surface, the force starts to increase. And at a deeper indentation, we see flattening of the force distance curve in this case. Then, just before we hit the glass surface, which we can see here at the end, we see two small discontinuities. And these continuities actually reflect the penetration of the two lipid bilayers. Now, this signature can, for example, be used to distinguish an EV from any other particle, because if you don't have lipid bilayers, you don't have these signature discontinuities. Then, when we retract the cantilever tip, as shown here in blue, we can see that a slightly different response, and also we can see that there's adhesion of the tip to the vesicle. So you can use these curves to fit the stiffness, as also illustrated in the graph. But since you have a not entirely linear response, this stiffness does depend on the chosen fitting interval. So stiffness is actually an extrinsic property, and it depends not only on the mechanical properties of the EV, but also on the size and the shape. And this is a reason why people often report different mechanical properties, such as a Young's modulus. Because in principle, this is an elastic modulus that is independent of the size and shape, but just a measure of the actual material properties of what the vesicle is made of. So these parameters are also obtained by fitting the force deformation curves, but the formula depends on the chosen mechanical model. And this often involves additional assumptions about the particle property. So some of the assumptions that are commonly made using these type of analysis are that the response is fully elastic, so there's no viscous deformation, that there's no adhesion between the tip and the vesicle, as well as small deformations compared to both the size of the EV as well as the size of the tip. And so this comes down that only really the first bit of the force deformation curve should be fitted. I will briefly discuss a couple of these models, the ones that are most frequently used. For a more in-depth discussion, I would like to refer you to the recent review at the bottom of this slide. So the Hertz model is frequently applied, perhaps mostly of its simplicity. So this obtains a Young's modulus for the particle, and it is important to know that this model assumes a uniform, isotropic, and fully solid spherical particle, as illustrated on the top right. Now, examples of where this model would be appropriate are, for example, a solid rubber ball or an iron ball. But in contrast, EVs consist out of a membrane and a fluid-filled lumen and are clearly neither solid nor uniform. This model further assumes a specific indenter shape, but it has adaptations for various indenter shapes. A related model is the thin shell model. This also obtains Young's modulus and also assumes that a solid, uniform, and isotropic material, but now it assumes that there's just a thin hollow shell, as shown on the bottom right. So this model is likely to find a much higher Young's modulus than the Hertz model because this reports a Young's modulus for a thin membrane instead for a solid sphere. So some of these assumptions that are made for these models are very strong and even clearly violated. In this case, we still may be able to speak about an effective Young's modulus. However, the reported values will likely not be fully independent of vesicle shape and size, which means that we need to be careful in comparing these values between samples and between studies. It's also important to note that some AFM imaging modes allow you to directly obtain a Young's modulus during imaging, essentially because during imaging a force deformation curve is made at each sample point. This is true for the sub-resonance tapping modes. They typically use the Hertz model that I discussed above, and while convenient, be aware that this is still prone to the same pitfalls and the same assumptions. Using these imaging modes to derive mechanical parameters also gives you less control over the fitting interval and less insight into the goodness of fit than if you separately make force indentation curves. Finally, a different model for describing vesicle mechanics has been introduced by myself and colleagues. This one is based on Kenham-Held theory for fluid membranes. So unlike these other models, it doesn't derive a Young's modulus, but a bending modulus, a measure for the bending resistance unique to membranes. So similar to the thin shell model, it assumes that the outer shell is the only structural contributor to the EV mechanics. But unique among this model is that it takes the fluidity of the lipid bilayer into account, meaning that it doesn't treat the lipid bilayer as a solid or isotropic material, but as a 2D fluid, which is likely a more accurate physical description. Moreover, this model accounts for pressurization of vesicles. So during spreading, since the surface area of EVs cannot expand, the volume will have to shrink, leading to an osmotic pressure over the membrane. This is ignored by the previous models, but studies using liposomes and EVs have shown that this is in fact a strong determinant of the vesicle mechanical properties for adherent vesicles. So this model was shown to accurately describe even deeper indentations of EVs derived from red blood cells. However, it does require much more elaborate experiments higher sample sizes and looking at both the indentation and retraction curve, and is therefore the most time consuming and not easily scalable of the measurement approaches. In the context of polydisperse samples, the ISEV approach, which measures single vesicles at a time, allows accurate description of the heterogeneity in the sample. However, the relatively low throughput will make detection of rare vesicle types more challenging. Moreover, it's good to keep in mind that the vesicles we want to investigate need to be attached to the surface. So if there are differences in our vesicle population or EV population, for that some EVs stick better to this surface than others, we may be pre-selecting for a certain subpopulation of vesicles. Some more practical information for performing AFM experiments. So the throughput I already briefly mentioned on the first slide, but it's relatively low. AFM can, to my knowledge, not be easily combined with autosampling. AFM can identify EVs based on the mechanical behavior, those two discontinuities that I described a couple of slides before, or based, for example, on the shape, or, for example, when combined with fluorescence microscopy. The requirements of the EVs to attach the EVs to a glass surface makes the method restricted to in vitro use. And currently, the throughput is relatively low for real-time characterization, but this is possible. In terms of assay controls, so currently no broad standards are used as a reference. If you are getting started with AFM, I can strongly recommend to also perform some experiments on small artificial unilamellar vesicles, or SUVs, of a known composition and a known size. This would be a good starting point and reference to use. In addition, one thing that I didn't discuss yet, but what is a good control during experiments, is to sometimes also, especially for mechanical measurements, is to sometimes also indent the glass surface next to the EVs. So the AFM tip can become contaminated with EVs, parts thereof, or other particles present in the sample, and these can strongly affect your measurements of both the shape of vesicles as well as during the indentation. For example, at some point you might be indenting a vesicle with another vesicle. So when you indent on the glass surface, you can easily detect if your tip is contaminated, because what you should observe is a linear slope that reflects purely the cantilever response, no force drops. If you suspect contamination of the AFM tip during an experiment, you can best replace your AFM tip. Since AFM is still emerging as a tool for the study of EVs, general guidelines for what should be reported have not been really established. I would suggest the following. Always make clear whether you're operating in fluid or in air and which imaging mode you're using. Report your tip size and material, as well as the stiffness of the cantilever you've used. Also, provide the calculation method for the derivation of the size that you use, and provide an additional indicator for the shape of EVs, so the degree of spreading on the surface. And this can be, for example, the contact angle, the full width half maximum, or the height divided by the radius of curvature. For mechanical measurements, in addition, it would be recommended to indicate the indentation speed, because this can affect the mechanical measurements. The mechanical model that you use to derive the elastic moduli, for example, the Hertz model, the thin shell model, or the Canham-Helfrich theory. Report the fitting interval, and also provide some examples of the indentation behavior. So refrain from just reporting the median, mean, and mode of either the height, diameter, or Young's modulus of particles. Some explicit tips are also summarized on this slide. All of these I've already mentioned during the presentation. So since AFM use for EFE characterization is still in its early days, multiple exciting applications are still under development. This includes effort to gain more information for AFM measurements or those enhancing the throughput. The new approaches for mechanical characterization based on images and vesicle shape alone, and by making assumptions about the adhesion energy between vesicles and their substrate, can perhaps provide much quicker analysis of basic vesicle mechanical properties. In addition, AFM tips can be functionalized with, for example, an antibody, which can then help identify certain vesicle population or presence of specific molecules on EVs. These specific interactions can be detected during withdrawal of the AFM from the surface because they cause additional adhesion between the AFM tip and the EV. Finally, AFM can be combined with other powerful techniques. An example is that the tip can sometimes enhance the resolution and signal magnitude of other techniques, such as Raman spectroscopy, a technique for chemical analysis. This currently requires advanced setups, but has the potential to perform chemical composition analysis of single EVs in a label-free manner. I would like to point you to the following published work that I referred to in this talk, but are also a great starting point for further reading. Thank you so much for your attention, and good luck with using AFM to characterize your EVs.